I always like to do it in your guys' class because by the first one, there's like things that I decide I'm going to tweak, and by the third one, I'm getting tired. So when I record it, I like to record this class. All right, so we're going to go through each one of these quantum numbers. We're going to talk about, what's given here is the name, the symbol, and then we're going to talk about what they physically mean, like what do they mean in reality within the atom space, and then their allowed values, meaning like there's certain ones when you're closest to the nucleus that are there. When you get further out from the nucleus, you get more and more of these regions where the electrons live. Remember, we call those regions where the electrons live, we call those the orbitals. So not orbit like it's moving around this thing, but orbital meaning a physical three-dimensional volume. So all of the space in this picture we're going to show you is the orbital, and that's where an electron can be. And highlighted down here, in each of these orbitals, 2 electrons can be in each orbital. Okay? So the first 3 quantum numbers are going to tell us which physical region of space are those electrons, and then 2 of the electrons can be in each of that region. Okay, so the first one, principal quantum number, really means, the biggest thing it means is the distance away from the nucleus. So if I have n equals 1, n equals 2, n equals 3, the bigger number means the outer edges of that region of space, that orbital, are further away. It's not that the electron is limited to that distance away, it's that the outer edges are that far away. So in the lowest energy orbital is a sphere, so think of like a ball, and the electron can be anywhere inside of that ball, but it has like an outer limit. The next one, the n equals 2, also has a spherical orbital where the electron can be anywhere inside of that ball, but it is a little bit bigger. So think of like nesting balls. One that's small, one that's bigger, one that's even bigger. So n equals 3 would be larger, but it still can be in that entire volume inside. Okay, so that's the n value. We talked a little bit, I think, about different shaped orbitals. So we talked about how there's a sphere, and then there's also this like dumbbell shape that looks like this. I'll just go scroll to it really quick. That one. So if I had the spherical shape and the dumbbell shape at n equals 2, their outer edges would be the same. So look, I'm not changing where the outer edges are, I'm just changing the shape. This one's a sphere, this one's a dumbbell shape, but their outer edges are still the same distance away from the nucleus. So they're still both n equals 2. Okay, so I'm going to start an energy diagram for us, meaning like the nucleus is down here, and as I draw horizontal lines going up, they're going to be lower in energy down here and higher in energy there. That's what this arrow is telling you, is that the energy is increasing the further we're getting up here, which should make sense because we said that the closer something is to the nucleus, the lower in potential energy it is. So n equals 1 is down here. I'm just, instead of drawing a line or anything, I'm just going to write. So n equals 1, n equals 2, n equals 3, n equals 4. Okay? So we call each one of these shells. So we would say like the 4th shell. Again, just the 4th layer out for the outer edges of these orbitals. I just use the word shell. It's on the notes there, but that's probably the more common, rather than just saying principal energy level, using the word shell is the most common way to refer to it. And we just said the larger the value of n, the more energy. Also, the larger the orbital, the further its edges are out from the nucleus, and so that's going to be a bigger ball or something that's being added. Okay, that one's relatively straightforward, I think. The next one, the angular momentum quantum number. So this is abbreviated by an L. We always write it cursive. I don't know why. We just do. So this one, the physical meaning is the shape. So a sphere is going to have a different L value than the dumbbell shape. Okay? And to make matters more confusing, we give the number for the L value a letter. So let me explain why we do this. If you had something that was n equals 2 and L equals 0, and you wanted to quickly tell people n equals 2, L equals 0, that's kind of a mouthful. If you were to say 20, do I mean 20 or do I mean 20? So we give letter designations to the L so that we can quickly describe the N and the L without getting confused about, is it part of the previous one? Is the 0 the L value or is the 0 part of the N value? So 0 we say is S. So I'll write look, you have that there. I'll write a chart for you guys. It's up there, but 0 is S, 1 is P, 2 is D, and 3 is F. Everyone's always like, what the crap? Why are we not just doing A, B, C, D? Right? Like that would be a lot easier. This comes from before they had really good measurement systems. What's the word I'm looking for? Whatever. Really good measuring devices, and they were visually looking at those atomic emission spectra. They would look kind of like blurry sometimes. Like sometimes they were very clear and distinct, probably if there was like a single wavelength in that region of space. Whereas if there were like a lot of really close ones together, they would kind of appear blurry. And so they would give these different names. I just blanked on what S was. P is principal, D is diffuse. I just said it in my other class. It's like my mind just went blank. It'll come to me in a second. Anyway, they labeled them based on how they appeared. So it has no meaning for us anymore because we have better measurement systems that aren't going to, we're not going to confuse the different lines. But it's just kind of a carryover from that time. So SPDF, SPDF, just run it through your mind a few times. We're going to keep using it. You'll use it by the end of chapter 9. It'll become pretty easy. You're not going to get them too confused, I don't think. But just recognize that the letter designation the number designation has simple, principal, diffuse. The number designation has a letter associated with it, and we will use that more often than not. Okay, so it tells us the shape of the orbital. We looked at S and said that that was a sphere. So again, I'm going to scroll back and forth. Okay, so S is a sphere. P are these 2 lobes. Sometimes we call them dumbbells. D's now have 4 lobes and some other funky looking thing. Okay, but for a given thing, whatever N value it is, if the L is equal to 2, it's going to have this general shape. If the L is equal to 1, it's going to have this general shape. Okay, so it tells us about the shape of the orbital. I don't think I have this written on there, but the shape does have an effect on the energy. I'm not sure why I don't have it written on there, but it is not as dominant as N. So N is the biggest factor affecting energy, but L does have a small effect on energy. That should be A, shouldn't it? This is how good I am with English. Okay, so the other thing we need to talk about is what are the possible values. So this says 0 to n minus 1. It means it's a range starting at 0 all the way up through 1 less than whatever the n value is. So let's do one of the higher ones right now. Let's say n equals 2. So for n equals 2, the L is a range from 0 to n minus 1. In this case, n is 2. 2 minus 1 is 1. So 0 through 1. Okay? Meaning L at n equals 2 can either be 0 or 1. So to indicate this, I'm going to draw some lines. L equals 0. L equals 1. And the reason I drew them different is because we just said that shape, or L value, has an effect on energy. It's not the biggest effect. N is the biggest effect, okay? But L does have an effect as well. So the bigger the L value, the higher that energy level is. For n equals 1, 0 through n minus 1, where n is 1, so 0 through 0, L can only be equal to 0 in n equals 1. Okay? So there's only L equals 0 in n equals 1. Moving up to n equals 3, L 0 through n minus 1, or 3 minus 1, so that's 2. So a range from 0 to 2. So 0, 1, 2. So you're noticing, hopefully, that every time the n increases, we get one additional L value. So again, L equals 0, L equals 1, L equals 2. And then finally, for n equals 4, now we're going to have L equals 0. I'm just staggering them this way so that I can draw other stuff in. The important point is how up and down I'm going. Because the higher up I go, the more energy it has. Now I'm going to have to tweak this. Let me just do it now. Don't worry about what I'm doing right now. We'll talk about it in a second. Okay, so L equals, this is me saying this is n equals 3. This is n equals 2, this is n equals 1, okay? All right, L equals 0, L equals 1, L equals 2, L equals 3, okay? So every n value we go up on, there's gonna be a picture that summarizes all of this at the end. So maybe don't try copying it and just watch me do it so that you can follow along and then you can look at the picture. I'll show it to you in a second. And this is we're gonna add to this as we go to eventually make it look like the picture we're gonna see in a bit by the end of class. Okay, so each n value you add another L value. It's another way of thinking of it. They always start at 0, and then they go up until 1 less than whatever the n value is. Also notice that because they start at 0, the total number of them are the same as the n value. Like in n equals 4, we have 4 of them. It's just that their actual number designation starts at 0, and so it's 0, 1, 2, 3 rather than 1, 2, 3, 4. Okay? So the highest one is 1 less than that, but there's 4 of them. So that's what it means when it says, I swear it says that somewhere, like the number of L values is equal to n. It'll probably come up in a second. Okay, so when we combine the n value and the L value and like talk about them together, that's called the subshell. So remember, each of these has a letter designation, so I'm going to write that there as well. So these guys are known as S. These are P. These are D, and those are F. Okay, so we can talk about the 2P subshell. That would be this area here, okay? I'm gonna add to this subshell. because there are actually 3 orbitals there. Shouldn't be that surprising because when we looked at the picture, we saw 3 of them. We're going to explain why in a second. But all 3 of them actually have an L value of 1. So all 3 of those would be considered the 2p subshell. 2 because it's N equals 2, P because the L is equal to 1. Or like this one would be the 4D subshell. Again, the letter designation for L just because it makes it easier to talk about. Okay, and then the energy is changing as well because of the shape. I feel like I'm going to change this question because we already did this. So it says, what values of L are possible for N equals 3? Okay, so looking at our chart over there, for N equals 3, we can have 0, we can have 1, we can have 2. Those are our N values, or L values for N equals 3, so this one. Okay, so what about for N equals 7? Tell me what the possible L values are. Just write them down. I'll give you a minute to do that. You're totally lost, just refer back up here where it says allowed values, or try to go off the examples of the ones I've given already. So much of like grasping difficult information is like persistence, because if you just look at it and you're like, I don't know what you're talking about. Okay, but go look for additional things to help you understand what we're talking about. Okay, so 0 through n minus 1. So start at 0. So L could be 0. It could also be 1, 2, 3, 4, 5, 6. So up through 1 less than the n value. Now, we don't have letter names for the higher ones. We just have SPDF. If you wanted to give them letters, then we would say G, H. We like continue on alphabetically. But you're never going to see ones above F, so that's why you don't really have to worry about it. Okay, remember that means this one is a sphere. So again, this is an indicator of shape. It's the lowest energy one. 1 is a little bit higher in energy. It's the dumbbell shape. 2 is even higher in energy. And it's the one that has like 4 lobes, except for the funky one. So I'll say 4 lobes, okay? And so forth. I don't know if I have a picture of Fs. I'm sure there's one in your textbook. They end up having 8 lobes, most of them, but then they also have like one that's 2 that has like 2. What is the plural of torus? It can't possibly be tori, is it? Torus is the mathematical word for a donut shape. Like tori, 2 tori. Anyway, maybe we'll look at Fs eventually. Okay, so that's the L value. Has a little bit of an effect on energy, tells us about the shape, and starts at 0 and goes up until 1 less than the n value. All right. Are you totally lost yet, or you feel like you're following along enough? You're probably thinking, why does any of this matter? Or like, what is it going to mean? What are we going to do with it eventually? So maybe let me pause and like give you some context for a second. So, okay. So the only thing about this image that I don't like is that it doesn't show that these guys are like a little bit higher in energy. And then these guys are even higher in energy. Otherwise, it's a pretty good description. There is a better one right here. So it's starting to fill in. The N value is written first. The L value is written as a letter, but it's also written up here. So all of these guys are S's, and that's why they're an L of 0. All of these guys are P's. That's why they're an L of 1, and so forth. We haven't talked about the numbers underneath yet. We're going to get there next. But what this is trying to describe to you, that's what I've started drawing over there. What this is trying to describe to you is the potential places where the electrons can be. So if you, maybe we should do this one. I didn't do it in my other class because when we start to like overlay these, they feel kind of meaningless, but let's give it a try. Okay, ignore the fact that you see like dark areas in there. Just look at the outer edges. So this would be the S. I guess you could kind of, no, I don't want to do that. This would be the S orbital in n equals 3. And now I'm going to switch to a p orbital in n equals 3. This is not going to have meaning. I got to go to n equals 2. Okay, this is the s orbital, and this is the p orbital. Okay, I'm just rotating it so you can see different areas. They look a little bit more like balls and kind of these shapes, less than like the lobe shapes, the dumbbell shapes, but close enough. Okay, so we're saying that an electron, when we draw these lines, we're trying to describe these physical regions. So we could have, and as I said before, we can have 2 electrons in each of these orbitals. So we could have 2 electrons in n equals 1. It's pretty hard to see this, but n equals 1, L equals 0. We can have 2 electrons in that space. If there are only 2 electrons in the atom, like helium, that's where they're going to be. They want to be as low in energy as possible, as close to the nucleus as possible. If I have 3 electrons, though, like in lithium, then we're going to have to step up in energy, and that's when we go to n equals 2, but we stay at L equals 0 because that's the lowest in energy. Once we start to get like nitrogen, oxygen, so like 4, 5, 6, and 7 electrons, now we start having to go into the L equals 1, or the p orbitals. There are 3 of them. I don't think I can show them at the same time, but the only difference between the 3 of them, and this is good because this leads us into m equals m sub L, the magnetic quantum number. Okay, so I'm trying to line this up so that, do you see how the x-axis is going to be the one that's coming out, and the y is, normal, vertical, and z is this way? Usually z is the one coming out. Whatever, I can twist it. So there are 3 orbitals that have n equals 2 and L equals 1. So I drew them as 3 lines over there. The way we differentiate those and the way that they're different is just their orientation. So we're going to have this one that's kind of along the z-axis. So it's like this, and it's flat in a sense, like it's lined up with the z-axis, okay? If we turn and have another one, so not turn, but actually look at another one. So I'm going to change this, and these have different designations. They call them X, Y, and Z. We're going to give them numbers. But if I look at the Y, now it's up and down, right? So there are 3 different orbitals, one that's this way. So I'll show it again. One that's this way, one that's that way, and then one that's like in and out of the screen. If I tip it, you can see that it's like supposed to be in and out of the screen. So we're looking down it, okay? So that is the different M sub L values. So M sub L is the next quantum number. Let me switch back over. So M sub L is the next quantum number. It has no effect on energy. And it is an indicator of which of the orbitals in a particular subshell you're talking about. So the subshell here would be N equals 2, L equals 1. And there would be 3 different orbitals with the following M sub L values: -1, 0, and +1. And physically what they mean is just which orbital are you talking about. Are you talking about the one that's pointed this way, or the one that's pointed this way, or the one that's pointed that way? But they're all equal in energy. Oh, it's right there. 3 equal energy orbitals. So let me go back up to this M sub L description page. Okay, the physical meaning is the orientation of the orbital. So like how its direction in space, I think is what I said. So how it's like lined up and how it's different from the other ones in that same subshell. But there is no impact on energy. Okay, we're going to talk about the possible values, and the values are a good way to indicate which one we're talking about, which orbital we're talking about, but they also tell us how many orbitals there are in a given subshell. So the range is again dependent on something else. It's dependent on L, and it goes from -L to +L. So if L is equal to 1, M sub L could be equal to -L, 0, +L. So that's why I said there's 3 orbitals in the N equals 2, L equals 1 subshell, and this is true of any L equals 1 subshell. There's 3 orbitals. We would designate them as -1, 0, and +1, but maybe even more interesting than the number themselves is how many there are. So L equals 1, which are p orbitals, always have 3 of them. So in fact, I'm going to come over on our picture here. And in addition to the L equals 1, now I can write M sub L equals -1, M sub L equals 0, M sub L equals +1. Well, what about L equals 2? Ooh, what's the next question on the next slide? What's my example one? I can't touch it and scroll. There we go. Okay. So answer this and then we'll do it together. What are the possible M sub L values if L equals 2? Remembering that the range is listed up here, -L through +L. It's that easy. Start with the negative, go all the way through, integers, including 0, all the way up to the positive. So sure, that's great. There's those numbers. There's 5 of those numbers, though. What that means is that there are 5 orbitals. Or another way of talking about that is saying that in a particular subshell where L equals 2, we can hold 10 electrons. because that's the whole point, is that we want to know where are the electrons. Every orbital can hold 2 electrons. So if I can describe the N, L, and M sub L, I am talking about a particular electron, because those three, the particular orbital, those 3 quantum numbers are all together describing an orbital, okay? So we said that P's have 3, so I'm gonna go ahead and finish that. And then L equals 2 has 5. 1, 2, 3, 4, 5. So we would say M sub L equals -2, M sub L equals -1, M sub L equals 0, M sub L equals 1, M sub L equals 2. Okay? So there's lots of orbitals that have an M sub L of -1, but there is only, let's say this orbital, there's only one orbital in every atom that's going to have an N equals 3, an L equals 2, and an M sub L of 0. So if I want to talk about this particular electron, I can define where that electron is and what energy it has by talking about its N, L, and M sub L. So it is like we're making an address for each electron. We're making a spot by, if we give it those 3 numbers, we can say right where it is. And that's going to tell us a huge amount about its energy, its potential reactivity, how likely it is to either gain electrons or lose electrons based on what orbitals are empty still. So like maybe we have an atom where all of these orbitals are filled up and this one is still empty. That potentially could mean that electrons might be attracted there. Or if we compare 2 atoms and we look at what electrons or what orbitals are filled in, maybe that tells us where an electron might leave from. Okay? That's where we're headed with this. That's basically what chapter 9 will be, is saying we have this particular atom. Where are its electrons? And then eventually, how is that going to affect how big the atom is? How is that going to affect how easily it'll lose or gain electrons? All of this stuff. Because we've told you since the beginning of the semester, like metals tend to lose electrons. Non-metals tend to gain. Like now you're going to actually have an understanding of why that's the case. Okay, the last quantum number is M sub S. And this one doesn't have anything to do with the orbital itself. It has to do with the electrons in the orbital. So every electron now is going to have a unique set of 4 quantum numbers. So if I had 3 electrons in an atom, like lithium, I could make a chart of electron 1, electron 2, electron 3, and list out a unique set of 4 quantum numbers for each of those electrons. Basically saying, where are those electrons in the atom? This is a little bit crazy, right? Like, for goodness sakes, we're talking about these teeny tiny atoms, and now we're going even deeper and talking about their electrons and saying, are they here or are they here? Or are they here? Like, do we really care? Yes, we care immensely. It makes a big difference in chemistry in general. Yeah.
Can you explain real quick what the principal level by N is?
Yeah, so distance from the nucleus. So let's just stick with the spherical ones. So this would be N equals 1, L equals 0. This would be N equals 2, L equals 0. This would be N equals 3, L equals 0.
So all the balloon, all those orbitals are only within L?
The L tells you whether they're balloon shaped or whether they're sphere shaped. So the N tells you this. The L tells you, is it this or is it this? And then the M sub L tells you, is it this one, is it this one, or is it this one?
Okay. And then there's a further one.
No, that's it for the orbitals. The M sub S tells you there can be 2 electrons in each orbital. Which one is it? So So we can differentiate the two electrons by a thing called spin. And this is the only one that's not an integer. It's plus 1/2 or minus 1/2. So we could have two electrons where n equals 1, meaning they're the smallest one. L equals 0, which means it's a sphere. Now with m sub L, when it's 0, it's just 0 too, because there's just one of them. It doesn't have a different orientation. One of the electrons would have a positive 1/2 spin, and one would have a negative 1/2 spin. So I like how we did this. Let's do this one more time. N is this, or this, or this. L is this versus this. And M sub L is this versus this versus that. And M sub S is, there's two electrons in here. Which one are we talking about?
Why didn't you use the 3D part on that example?
The which?
The
3.
example that you just did, you just used 1E and 2E.
In this example, because if I only had, let's say, 2 electrons, they're always going to go to the lowest energy one. So in this picture, you would never, like if you had 2 electrons, you would never place them, let's say, up here. Okay, so now I have to tell you how we draw electrons. So we draw electrons like arrows when we're doing these energy diagrams. We're lazy though, so we just have one little, whatever that's called, one little side to the arrow. And we draw one up to designate plus 1/2 and one down to designate negative 1/2. So if I was drawing electrons here, I would never draw them like both up here because that's so high in energy. And if I only have 2 electrons, they're always going to start at the bottom and then fill in. So, and in fact, let me use the other picture because it's a little bit better in differentiating the energy. So if I had, and this is where we're headed with this in the next chapter, if I had 17 electrons, okay, I would know their location because there's 2 in each orbital and they're going to start at the bottom. This is called the Aufbau principle, is that you start at the lowest energy one and fill them in sequentially until you get to higher energies. So let's say 17. So 1, 2 are going to be in the 1s. 3, 4 are going to be in the 2s. 5, 6, 7, 8, 9, 10 are going to be in the 2p. I'm saying the 10th electron, not 10 in the 2p. 11, 12 in 3s. What did I say, 17? Okay, I'm safe. What did I get to? 10, 12, thank you. 13, 14, 15, 16, 17. So 17 corresponds to chlorine. That is exactly where the 17 electrons in chlorine would be. 2 of them would be in 1s. 2 of them would be in 2s. 6 of them would be in the 3 2p orbitals. 2 of them in the 3s, and then 5 would be in the 3 3p orbitals. Because we start at the lowest energy and we fill them in terms of their energy. Now the other thing, we don't do this, we do this in a shorthand way that we'll get into when we get into chapter 9. But we could, in theory, make a chart like this and say where each one of those electrons are and what their 4 quantum numbers would be. So they would all be unique. They can't have the same set of quantum numbers. So let's actually, I'm going to write it down at the bottom because that's where the 1s are listed. So these 2 would be what the 1s electrons are here. So it would be like 1, 0, 0. That's the orbital. And then the m sub s plus 1/2 and minus 1/2. So those are the ones in the 1s orbital. Why? Because n equals 1, L equals 0 because it's an s. M sub L is always 0 for s orbitals because there's no other choice. And then we would move up to 2s. And then it would be n equals 2, L equals 0, M sub L equals 0, M sub S is plus 1/2, and minus 1/2. It's very uninteresting when you're talking about every single little electron. It's more interesting when we draw these diagrams and then we can highlight a particular one. Let me go one step further to the 2p's. I'm not going to do all of these. Okay, so if I step up to the 2p's, now 2, n equals 2, but L is now 1. And M sub L could really, we could talk about, it doesn't matter which ones we talk about first. The natural, like traditional way is we start with the negative. So we would say this is -1, but we have 2 electrons in that orbital. How do we differentiate the 2 electrons? We say one has a positive 1/2 spin, one has a negative 1/2 spin. So in the Schrodinger equations, the quantum mechanics equations, every single electron is defined by a mathematical function. So the results of that function are these values, and these 2 electrons, for example, would have the exact same results for N, L, and M sub L, and they would only differ by the spin value, but they would still be different. I feel like I need a second to let that sink in. And then we could keep doing this for N equals 2, L equals P or 1, 0, and for positive 1, and so forth. And we could list all of them if we wanted to. Okay, what does spin mean? It does not mean the electron is spinning. I don't care what a textbook shows you or tells you. We don't know the behavior of the electron, period. We cannot tell that. We can tell its energy. We can tell sort of its location. Tunneling electron microscopes can kind of see the influence of the electron, but we do not know about how it's moving because we can't even describe it as like, is it a particle? So we certainly can't say like that it's moving in a particular way or spinning. There's a law or a theory called the Heisenberg uncertainty principle. It says we can't know the exact motion or position of the electron. The better we know one, the worse we know the other. So we call it spin because mathematically it appears the same way that a spinning top would be described when we look at like its angular momentum, really is what we're looking at. It appears like a spinning top, like a toy, you know, or a ball, whatever, something that's spinning around. Mathematically, it appears that way. We can't know physically what it's doing. So we call it spin, and we say it has a value of 1/2, meaning corresponding to all the other things. It's half as large as something else. Okay? One of them is directional in one way, and one of them is directional in the other. So they're opposite each other, which is why one is positive and one is negative. But as far as physical meaning, it doesn't have a whole lot of a physical meaning for us. Okay, let me see what else I want to talk about that may be close to the end. We'll see. Oh, there's the pictures of the Fs. I do have them in there. Yeah, I think the only other thing to talk about is to recognize that, let's talk about shape for one more second. So we said that the p orbital is higher in energy, right? We said an L value of 1 is higher in energy, but we didn't talk about why. So everything we've ever said up until this point is that the closer the electron is to the nucleus, the lower its energy. So if I have a sphere where the electron can be anywhere in here and the nucleus is in the middle, that has, I like to call it access to the nucleus. Your textbook will call it nuclear penetration. But access, like it can get really close to the nucleus because it's a sphere, right? It has all those 360 degrees around it. When we go to p orbitals, they're shaped like this. And guess what? The only place where they can go to be really close to the nucleus is right here and right there. Okay? So their access to the nucleus, their ability to be close to the nucleus, is significantly less than a spherical shape. And that is why the s orbitals are lower in energy than the p. The d orbitals are even more dramatic. When we look at the d orbitals, they kind of go a little, their ends go a little bit further out away from the nucleus than the p's do. And so they have even less access to the nucleus. So much so, you don't have to follow with me. I'm going to jump ahead quite a bit. So much so that the d orbital, is that the picture that I wanted? No, just ignore that. That the d orbital in n equals 3 is actually higher in energy than the 4s. So I fixed this a while back and I said, don't worry about what I'm doing. So the s orbital is so good at getting close to the nucleus that it actually, even though it's n equals 4, will actually have more ability to get close to the nucleus than the n equals 3, that's this funky D shape where it has very little ability to get close to the nucleus. Even though its outer edges are bigger in the n equals 4. So it creates this weird thing where the n equals 3 will fill the s, the p, and then it'll jump to the 4s and back to the 3d. Okay, so we'll cover that in detail when we get to chapter 9, but the shape has a huge influence on energy because it limits or allows access to the nucleus so that negative charge can be closer. Okay, so you technically have everything you need to do the homework. So what I would say is get a good start on it. Try some of the problems, like struggle through, look at examples over the weekend. But then we'll practice on Monday, and you guys are welcome to bring any questions in too, but we'll do lots of practice problems on Monday. Have a good weekend. Hi. I did. It's still recording, in fact. Yes, and I will post it. I hope when I walked over there that it's still